So today our speaker is Sebi Huber from ETH Zurich. You may know him for many different interesting results in the field of cold atoms and machine learning in physics, but today he will talk about his very cool stuff of topological mechanics and topological materials. So with that, Sebi, go ahead, share your screen, start whenever you're ready.
Oh, I didn't start sharing my screen. There we go. Oh, okay, thank you, Eliska, for the introduction, of course, the invitation. Today, I'm playing with my light here. Today, I'm going to give you an evening treat on topological mechanics. And well, let's first say that we do that in Zurich with a wonderful team. You see here the group as it was last summer up in the tree. Many of the names will show up during the talk on the slides. Also, someone is paying for all of that. That's the Swiss National Science Foundation, and the Europeans also contribute a bit. Let me first start just to give a bit of a context and embedding in what we're actually doing in my group, and it helps put things a bit together in context throughout the talk. We are a group in the Institute for Theoretical Physics at ETH, so we think a lot, and when we think, we mostly think about the electronic systems. So that's kind of where our brain power is going, but we also do experiments, and that's indicated by these hands. So we actually do some actual labor, and when we do experiments, it's mostly with mechanical degrees of freedom. Today, it's, I think, almost exclusively sound waves. That's why we have this speaker here. So that's kind of experiments we do with classical waves, thinking we do mostly in quantum mechanical systems, electrons, and that's where our heart lies. You will have to decide for yourself at the end. Now, what binds these two things together largely is that we do things that, as title says, Felix Bloch could have done, and it's really mainly related to the fact that you have a plane wave in free space, and we know from Mr. Bloch up here that the moment you put such a plane wave in a periodic background, it's still a wave. You still have the nice wave character, but then you need to add an object that is periodic in space, and really what it changes your free space dispersion into something which we call bands. So that's we know for 100 years now, and of course but Felix Bloch mostly looked at these kind of things, and this is a fascinating change, of course, but we pay a bit more attention to how this function up here behaves as a function of k, and really the way I put it here should make it clear that it's waves in a periodic background, and whether it's now electrons in a solid or it's just sound waves in a periodically structured background shouldn't matter too much. So that's kind of what binds these two things we do in my group together. Now, maybe a few more words of why we are interested in classical waves, and I think there are two main things I would like to point out. One is, of course, the moment it's classical waves, the route to applications is a much more easy one than the one if you do quantum mechanics, because you don't need to be cold, you don't need to be very careful, it just works. And I think that drives a lot of our activities here. And then if you have the benefit of having really smart engineers in your group, you know, they really take it to some extreme ways of what you can do with classical degrees of freedom. And the other thing is, besides the fact that classical waves are much easier to handle, and so routes to applications are much simpler, you can also do a lot of fascinating physics. And that's just because they're also easy to handle. If you know, have an idea, you want to see, does something really check out that you know from a theoretical perspective, and then you just go to the lab, you build it, you measure it, and it's a simple platform, and it unleashes fascinating physics. And I show you just a few things here you can do stuff like higher order topological insulators. You can, and then what we hear today is more axial fields and fragile topology. So it's things that from a theoretical perspective might be new, and you don't fully understand them, and then you build them in the lab, and many things become much clearer. And I think that's our main motivation to deal with these classical waves, besides the fact that it opens up the route to applications. Now, I said, okay, Felix Bloch said, what happens to a wave if I put it in a periodic background? We can be a bit more precise, because you might feel, or those that are not dealing with classical waves too much, you might feel uneasy that I want to kind of bridge between topological physics in electrons and in classical waves. But really, it all boils down to the fact that if you have like a lattice system as the one described here, and maybe you have electrons on them, what describes the physics is your Schrodinger equation that you see over here, and most probably topological properties or interesting band properties will be encoded in the Hamiltonian that I write here in real space. You have some hopping from site I to j, you might have some orbital content. It's really the structure of this Hamiltonian which determines everything. Now, if you go over to classical systems and all of a sudden you say, oh, these are little balls, these are little springs, then it's just Newton's equations of motion. And of course, they're second order in time, and there is no I here. So it's different. But if the structure of this matrix that we had describing our tight binding problem before, you just describe by the dynamical matrix describing your Newtonian equations of motions. So most probably certain structures that you could have had in that age just carry over to this D. Observable effects will be different, but topological content most probably will be the same for many aspects. And there are limitations to this bridge, but in principle, you shouldn't feel uneasy having like me going back and forward between classical and quantum mechanical objects. Now, the one thing is okay, we do classical waves, that I already said, and the question is, what do I mean by we do classical waves, or we do topological mechanics? What is the thing we really do? And I think that's best summarized in this slide, where you have here the phonon dispersion in some material. Let's call this a material. And then your phonons typically are just linearly dispersing, and at some point they reach the zone boundary and max out that typically terahertz range. So that's just a material God-given. And what we do is we drill holes. Huh? I mean, that's our expertise. We're very good at drilling, or I'm not sure whether we're good, but that's what we do. We drill holes. And the moment you drill holes, you have scatterers of your waves. And if you do it in a regular scheme, then you will get band structures like the ones over here. And it's really us designing how we do that to get to physics that we want over here. One nice thing is that the frequency at which interesting stuff happens is really at our disposal. It's, we make really big structures, it's hertz, and that was our first experiment with big pendula. We make it very small like we do now, then you get to gigahertz, depending on how small you make it. So that is kind of a scale that we can play with, but mainly it's the geometry that we play with. So that whenever I say we play with classical waves, that's what we do. So I think that's enough in terms of big overview description of what we're doing. And I would like to show you two examples how we capitalize on that interplay between doing experiments in classical systems and either learning something about quantum mechanical systems, or being pointed towards challenges that are then interesting in the other context. So it's always going forth and back. And here, in this example of axial fields in Weyl systems, it's really, we started out from a challenge for classical systems. We wanted to achieve something in classical waves, and we didn't know how to do. And we went on a shopping tour, if you want, in the quantum mechanical world. And at the end, when we overcame that challenge in that classical system over here, we actually were pointed towards an interesting open question, if you want, so in the quantum mechanical world. And the playground we're dealing with here are Weyl systems. So let me quickly just remind you of what Weyl system is. We know what the Dirac equation is. It describes the relativistic particles. If they don't have a mass, the 4-spinor of the Dirac equation falls apart into two spinors. And this is the equation that it describes. You have here the Pauli matrices, derivatives, and you act on a spinor that has two degrees of freedom. And in condensed matter systems, what this describes is really a band touching point, because it's linear, because of the linear appearance here. It's linearly dispersing around a point, and then this is just a 2D sketch, but it's in 3D, so you have 2 bands that touch here. Now we see that there is a blue and a red Weyl equation, and they differ by this sign here. And these are the 2 chiralities that you can have for your Weyl particles. And what it really means is, if you look at how do the eigenstates look like around this touching point, then either the spin or whatever degree of freedom is encoded by this 2x2 Pauli matrix is anti-aligned with the momentum around this touching point, or it's aligned. Nice result is that in a condensed matter system, of course, you did these Dirac points or Weyl points. They don't just hang out in the nothing. You always have to correct them somehow. In fact, in a lattice system, you're always bound to have a blue and a red Weyl point. At least you have as many blue as you have red ones of different chiralities. So these are just, it describes your band touching points in 3D. And they have various implications. One of them is this is in 3 dimensions in the bulk, 2 bands touch. If you look at what's going on the surface of this 3D system, then you look at the surface Brillouin zone, Kx, Ky, and then the projection of your Weyl points onto the surface Brillouin zone. You still have these touching bands, but then on the surface, you have an additional sheet, this golden sheet of excitations that starts at one Weyl point and ends at the other Weyl point. And for fermionic system, Fermi energy is something interesting. If the Fermi energy lies at the touching point, then you have a Fermi arc, meaning an open Fermi surface spanning from one side, one with projection of the Weyl point to the other. So that's just the standard thing what happens in Weyl points. But what I want to focus in this talk is for me, one of the more fascinating things that arise in such a Weyl system if you apply a magnetic field. And if you apply magnetic field, the spectrum changes from being 2 bands that touch. So we apply a magnetic field, let's say in Z direction, and then the system gaps out. But around each of the 2 Weyl points, we get a chiral channel, meaning on one place in the Brillouin zone, I only can go with in the direction of the magnetic field. On the other side of the Brillouin zone, I can only go against the magnetic field. And perpendicular to the magnetic field, I cannot move at all. So these are 2 channels that bring me through the whole sample in a unidirectional way, separated not in real space, but in momentum space. So that's unidirectional channels through bulk materials is something that, if you have like classical waves in mind, has potential for applications, because maybe you want to bring a signal from A to B in a reliable way such that it doesn't backscatter, stuff like that. So that's a very nice thing to have. And we asked ourselves, wow, that's cool. Let's try to do that in a system that has Weyl points in acoustics. But then the question is, well, that's how such a sample looks like. It's a piece of plastic. That the piece of plastic just gives me boundary conditions. And in between this plastic, I have air, and the sound waves in this air, well, that should be my Weyl system. That should be described by 2 bands, and they touch somewhere. The problem is, how do I apply a magnetic field? And of course, I cannot, because magnetic fields, they act on charged particles, and my sound waves simply are not charged. So that was the challenge, that we felt like we would like to have these unidirectional channels, but we did, at the time, we didn't know how to do that. And of course, the solution was out there in the electronic systems already. But let me first show you that you can do a Weyl system in acoustics and then import what people knew from electronic systems. And an acoustic Weyl system, you can, the Hamiltonian is here. It's very simple. It's a layered system of a hexagonal, of a honeycomb lattice, and then you have the next honeycomb lattice, and then you stack it more and more. And then you have just the hopping in plane, which is just a regular kind of graphene type hopping. Then you do AA stacking, where you just put the next hexagonal lattice on top, and you can hop straight up. And then you have this chiral hopping that you need to have indicated by these golden bars, which breaks inversion symmetry. That's an ingredient you need to have Weyl points. And the moment you implement such a tight binding model for acoustics, and this is really simple, because you should think of these black dots as acoustic cavities and the bars as channels connecting them. And once you do that, your 3D Brillouin zone looks like this. And you indeed find, if you solve the system, you find that you have two Weyl points at K and K prime, and then halfway up in Z direction, you have two other Weyl points that are in total of two red and two blue. So that a Weyl system we have here, that's the tight binding model. And that's the low energy expansion. And we should spend a second on that low energy expansion. Around each of these touching points of two bands, you can expand the Hamiltonian like this. So it's linearly dispersing, and you multiply it into the Pauli matrices. And then there is some velocity matrix. Maybe it's not just sigma dot the gradient, but there is some non-trivial mixing here, and you analyze all of those, and you find all kind of sign structures of this velocity matrix, and this gives you the different Weyl points. So that's the setup. That's easy. That's good. Now let's ask, how can we now apply this magnetic field? And this goes under the name of axial magnetic fields, and it can in solid state system be induced by uniaxial strain or other type of perturbations like magnetizations that you change as a function of space. But let's first do, what does it mean to apply a magnetic field? We all know that applying a magnetic field is really nothing but taking your K, your momentum, and minimally coupling a gauge field. So you just go from K to K minus E times A. But that's just what happens if you add the magnetic field. Now let's pick some gauge. I pick here a Landau gauge where I have K minus E by X, but we only take the EZ component, and then I add it to my Hamiltonian. But now I see I just have something that is in the EZ direction, so that is like KZ that multiplies into sigma Z in the equation before. So maybe here I have a KZ multiplying sigma Z. So if I add just the sublattice potential, that's just a potential. It's not a magnetic field. It's just a potential that makes a difference between the two bands, sigma Z. It depends on space. So I have a space-dependent sublattice potential, and then I call it by some name. If I add this sublattice potential to my low energy expansion of my Hamiltonian, so that's just the 4 Weyl points, depending on which V alpha beta I take, and I add this term. And if I now multiply it out, I see, oh, that's indeed the case. This indeed looks like a magnetic field, like we had it up here. It's just that somehow there is a plus and a minus, and all these plus and minuses stem from the fact that these different Weyl points have different plus and minuses over here. In other words, I have a field that looks like a magnetic field, but the sign is different depending on the chirality of the Weyl node. And that's what we call an axial field. And that's what has been discussed at length in the electronic systems. But for us, it's nice that we can mimic something that looks like a magnetic field. It's just a magnetic field that depends on which Weyl point you are in. But that's something we can do. The question is, how do we do that? You see now here a blow up of that sample. So everywhere there is air, the acoustic waves travel. We have this hexagonal structure that gives us the hexagonal lattice, and then these strange ventilator holes give us this chiral coupling that we indicated with as before. And then one mode is living here on this corner, and one mode is living on this corner of the unit cell. And if you make an acoustic cavity and you make it a bit bigger, you change its frequency. So by having here over this corner, you have a hole, and here you don't, that just means you have a sublattice potential, because that the mode that lives here has a different frequency than the one that lives here. Now you make this whole space dependent. You make this whole growing throughout the sample, and that's all you need to do to have a space dependent sublattice potential, which acts like a magnetic field per Weyl point, different for different chiralities. And once it's a bit of optimization, right? You need to find the right depth and size of these holes in order to really do a linear potential. But once you do that, you build your sample, you go scan, you shout at it, you excite it with the speaker, you have a microphone that you slide in, you make full state tomography if you want. And that's how it looks like, the dispersion curve looks like in momentum space. So here we're at the lower level, at this height in kz. And then this is a path through our momentum space. And you see these two bands, that's the lower band and that's the upper band. And then they touch here. And then and the same thing at kz equals pi half. And then we can zoom into these touching points where we hope to have opened the gap and have a chiral channel. And then if you zoom in and you make a careful analysis of your data, that this is now visually you can't see it as clearly, but the dots with the error bar should point it very clearly that here you only have left going ones or up going ones, and here have down going ones, and vice versa. So that was indeed, we achieved what we wanted. We wanted to have these unidirectional channels, and we implemented them for acoustics. The moment you have 4, there is something very interesting showing up, and that relates to the kind of the bridge over to the electronic systems, because most probably shouldn't make any rankings, but for me one of the most intriguing aspects of these Weyl systems are these non-local orbits in a magnetic field, because we thought at the moment the magnetic field, the two Weyl points open up a gap and give rise to these chiral channels, meaning if I sit in momentum space around one Weyl point, I can only go up through the sample. The moment I reach the surface, I reach this Fermi arc that I showed in the beginning. But we know that if we have a Fermi surface and we apply a magnetic field, you push your electrons along the Fermi surface. So you're sliding over here by doing Bloch oscillations, and you reach in momentum space the other Weyl point where you sink down to the other side of the sample again. So you have these non-local orbits where you go fixed in momentum space through real space. On the surface, you slide through momentum space, and then you go down and up and down and up and down and up. So that's a very fascinating aspect. So and also has been looked at experimentally. And the question is, if you have 2 Weyl points, it's clear what happens, because you can go up, you can go over, you go down. And now the problem arises if you have 4, and what happens with these non-local orbits. And that kind of gave rise to this something we didn't understand how this would check out also if you would now take your Weyl sample and bend it to induce that strain that would also give rise to that axial field. And let me present the puzzle that haunted us for a long time. This is now a sketch of the model that you see below. It's a slightly different model that is easier to handle, but it's in a sense the same as in you have 4 Weyl points, and 2 of them are red, 2 of them are blue, as it should be. And let's assume we apply an axial magnetic field where this red one is having a chiral channel that goes up through the sample, and this blue one has one that's going down through the sample. Because we do it with axial strain, let's say, or with the sublattice potential as we had before, you don't break time reversal. The moment you don't break time reversal, whenever there is a blue one that goes down, there also needs to be a one that goes up. So you actually all of a sudden have blue Weyl points that have a chiral channel going up, and one going down and one going up. And now it's not so clear what happens to these non-local orbits. In particular, if now your surface physics is like this, from this you have this additional sheet of excitations, connecting this red dot with this blue dot, then you in your non-local orbit, you come up, you're sliding over along this Fermi arc, and you reach this blue point, and then you sink down into the sample again. All good, like we had it with 2 Weyl points. Now let's change the model a bit or add a surface perturbation, because that's just the surface physics. You don't know from the bulk how the surface should be. You terminate a bit differently, you put something else on top. You might change that surface sheet like this. You still have a sheet of excitations connecting the 2 Weyl points. But now you see that on an equi-energy, or your Fermi arc really reaches from this red Weyl point again to a blue Weyl point, as it has to be. That's given by topology. But now you see that given the axial field you applied, you came up through the sample to this point, and now you're sliding along this arc, and now you're stuck, because now you're at the Weyl point where you can't go down, because this one also has a chiral Landau level that goes up. So that non-local orbit thing doesn't check out anymore. Moreover, the interpretation of that sublattice potential, or the interpretation of a strained sample in terms of a magnetic field, really only was true when I looked at the very low energy or around the Weyl point. Now, this and close in momentum space to that Weyl point. Now, all of a sudden, I have here an excitation that, or a sheet of excitations, or a Fermi arc connecting different Weyl points. That means I actually don't know. Should I interpret the strain or the sublattice potential over here in the middle as a magnetic field? Because it's not a magnetic field. In particular, it changes its sign from here to here. So that's something that really, I mean, we didn't know how to wrap our head around. But then, I mean, you just go and calculate, right? I mean, that's what you always should do. And it just did 2 things. One is we just did wave packet propagation. You take a real big sample, put it on the computer, and you just launch a wave packet in one of these chiral channels. And then the outcome is that, you know, you go through the sample, and then you come back, and then you go through the sample, then you stay on the surface for a while, and you see that this is real space. Whenever you stay on the surface, actually in momentum space, you move from one Weyl point to the other. So that's reassuring. If you connect the right 2 Weyl points with your Fermi surface, then actually you do slide over from this one to this. So despite the fact that it's not obvious that you should think of that as a magnetic field, you can actually push that analysis even further and look at the surface Green's function. From that, you can extract the local density of states. And there is a semi-classical formula that you see over here that tells you how should these sheets behave as a function of the strength of that axial magnetic field. And that formula really essentially assumes that you can think of that perturbation you added here along the arc and through the bulk as a magnetic field. And the fact that this is a plot without any fitting parameters, that this fits so nicely, that really means if you connect the right Weyl points, you can think of an axial magnetic field as a magnetic field also on the surface. Well, and things go down the drain if you connect the wrong ones. You see that you go maybe from one side to the other, but then you don't quite reach the other side. And you see here the 3D trajectories. And even worse, if you look at the local density of states pictures, then you see that doesn't resemble anything like this fan diagram we had before that corresponds to this non-local orbit. So that kind of summarizes what I wanted to say on axial fields. It was the driving for an unidirectional channel in a bulk material for classical waves. That's what we set out to do, what we wanted to have. And we found that one can do that with what people call axial magnetic fields, and we found a way to implement them in a classical system. And once you have that, you realize you always will have 4 Weyl points in these systems, because you can't break time reversal, or you don't want to break time reversal, maybe I should say. And then you immediately have 4 Weyl points, and that's a system that was not like super carefully analyzed also in the electronic case in terms of what does it mean for your non-local orbits, and that's kind of showcases a bit of how we work, how classical and quantum physics are actually not so different, and we mutually benefit each other. If at this point we have questions to what I was talking about until now, maybe it would be a good time. We can also go on and you ask me later.
I have a naive question about your resolution. What is the limit? Your 3D printer size, or here, yeah, for example?
Well, the resolution here. Is right, this your question?
Yeah, exactly. What do I have to do if I want to make this sharper?
First of all, don't you complain that this is not sharp enough? But no, it's not the 3D. Well, it is the 3D printer. Acoustic waves are beautiful because it's a scalar wave. It's easy to model. It's easy to cast things into tight binding models. It's brutally dissipative. And what you see here is in this direction, a blurring due to a broadening of our line width due to dissipation. And in this direction, it's also dissipation. You just have no K resolution because your wave packet dies actually halfway through the sample. That's why I don't show you results on the non-local orbits, because I can launch a wave packet on one side of my sample. It makes it about halfway.
I see. Yeah. Makes sense.
And I can blame the 3D printer because now we do similar experiments in metal cavities. I mean, people knew that. It's dissipation in acoustics you mainly have from surface effects, because you can talk to a person quite far away. So dissipation is not so bad for acoustics. But the moment you have small structures, it's all in the boundary layer where you dissipate, and then it's super important that the surfaces are smooth.
Thanks.
Anton, do you have a question?
Yeah, I do have a question. So what is the answer, after all, for the other boundary dispersion relation? So there are two modes that approach, and so it seems like on this description, on this level of description, there's a problem with the unitarity because there are channels only coming into the surface, and there's no adiabatic wave for a wave to reflect back.
Yes, but what it means, if there is a magnetic field, you're pushed forward in momentum space. But here you shouldn't think of a magnetic field, because the thing that looks like a magnetic field actually changes sign along the way. So at some point you just get stuck on that in your travel along momentum space. You get stuck because the thing that pushes you dies out, and then you just sit there on a chiral channel. And now you go in real space around the sample to the other side. So that's, but then you're always kind of confined to that, at least that's what numeric shows. You're confined to that region in the middle of that arc, and then you never quite pushed back into that chiral channel in the bulk. I think that's more or less what's happening.
All right, got it, thanks.
Do we have more questions? I don't see any more hands, so I think we can move on.
Okay, wonderful. The second part is fragile topology. It's, the link between the two parts is really acoustics. So that is what binds these two parts together. You will see here in the middle, we will do an experiment again in acoustics, but this time it's well, how should I explain that? I think I will present the challenge that I didn't understand, and then we needed to straighten our mind what all of this fragility is doing here. And then once we did the experiment, we got it all right. Well, we finally understood, and then it helped us to make progress towards that original challenge. I think the logic here is this way. It's a bit different, but it's still kind of that interplay. And the arena is one that this is a boring slide to show because everyone knows it by heart. For 3 years now, we have a crazy new platform that shows physics we didn't expect. Well, maybe we expected, but we were super excited to be able to play with it. And that's just twisted bilayer graphene. And in the magic angle regime, you have at certain carrier densities, you have a wonderful superconducting dome. And we try to understand that. Now I will present a challenge with respect to that, and then I show you how we try to answer it for us. And I said it's about superconductivity, and then the moment it's about superconductivity, you need two ingredients. You need to understand a lot of ingredients, but I think there are two main issues once you talk about superconductivity. One thing is you need pairs. Right? Someone needs to make your electrons behave like bosons, really, or at least a variant thereof. So you need a glue that makes your single electrons bind together, and this we know for a long time. But having pairs isn't quite the whole deal, because when we talk about the superconductor, we really mean how does it react to a magnetic field, and then you need to talk about the London equation. I apply a gauge field, and I want to get the current out. And only if there is a reasonable relation between the two, we should talk about the superconductor. And that's like one challenge is who is binding my electrons, and then the other thing is how does it react to a magnetic field. Now the good thing is that our forefathers already answered what is the superfluid stiffness, and it's just given by E squared, the density of these objects divided by the mass. So that's the superfluid stiffness, as we call it, and it relates how much current you get when you apply a magnetic field. Now, in the following, I will not talk about how the hell are these electrons bound together. So I'm not going to attempt to even answer in twisted bilayer graphene, why do you form pairs? Now, that's a debate I don't want to get into. I want to work a bit here, and why this is interesting. Here you see the band structure of magic angle twisted bilayer graphene. Actually, it's the band structure of an original model that doesn't take into account certain parameters that would make a gap here. But the point is really, this is the band that is interesting, and it's damn flat. And the moment something is flat, the effective mass is going to infinity. Now you take this formula over here, and you send m to infinity, your superconductor is going down the drain. And that's the challenge we try to address or try to understand. And of course, that's a linear response theory, so that's easy to do. And it's just the point that there is more than a spherical cow. Like the formula that I showed you before is just the first answer to the full one. And for that, we quickly need to look at this formula. The superfluid stiffness is really just the second derivative of the free energy with respect to the gauge field. I mean, those that know everything, it's clear why it's two derivatives. One is just that's how you couple the gauge field, so you get linear response with respect to that, and then you want to have the current operator coming down, and that's the other derivative. That's everyone should know that. Now, evaluating this is of course is impossible, because taking derivatives with respect to the free energy means you know the free energy, and typically you don't, because you don't know how to solve your system. But we can do that in mean field, and that's a very important point I need to make here. From now on, for the next 5 slides, everything is based on that mean field result. And it's actually at the end, I say, look, mean field is really stupid, and we need to do better. I'm not saying mean field is stupid, but I say mean field is nice, but we need to check what it's worth. So if you do that, then you get 2 terms. Now, the first one is just that spherical cow. If you assume that you have just a spherical Fermi surface in a quadratic band, then that's what you get from the mean field analysis. However, in the meantime, we know, I alluded to Felix Bloch in the beginning, that you know, we don't live in quadratic bands only. There is more to modern bands, or to interesting bands. And if you take into account, if you take the band content seriously, you find a second contribution. It has some horrible, energetic prefactors that I'm not so interested in. And it has this additional term which encodes the geometry of the band, which encodes this U of k and n that I said we like playing with a bit more. And in a sense, you can further massage this, because that's really, it's just a letter. What this is proportional to, it is just the width of the Wannier functions. So here we have a band contribution which is encoded in the properties of the Wannier functions. And that's more than just that band curvature effect, it's a band geometry effect encoded in the eigenfunctions. Now, we need to talk a hunch more about that, because I don't want you to all know what the Wannier function is. So let's do that. So we've seen that in the linear response theory, if you take it seriously, that you are not in free space, you have this additional contribution to the superfluid stiffness. Now, what is the Wannier function? The Wannier function is n of r, that's in the nth band, the Wannier function that lives at r. It's just the Fourier transform of our Bloch wave functions. Now, in free space, the Bloch wave functions are just e to the ikr. And if I take the Fourier transform with respect to that, so I see that I just get a delta function. So the Wannier function in a simple boring band that doesn't have any structure is just the delta function. And we see that the width of this delta function is just 0. That means it was okay for our forefathers to just drop these terms if they say we live in a spherical Fermi surface with no band content. But now let's think of what happens if you have a bit more interesting band. I make here two types of orbitals that my particle might hop in between. And then my Bloch wave function, of which I take the Fourier transform, has a weight in this orbital and the weight in that orbital, times that exponential factor that we also had up here. But now, if this isn't just a constant and boring, then my Wannier functions are just the Fourier transform of this object here. And the moment this is not just flat in k-space, if there is any k-dependence, then my Wannier function is extended. And the moment my Wannier function is extended, I cannot neglect these band effects. And that's a very important observation. And now I want to bind it to topology. And those of you that never heard of topology most probably wouldn't come to that colloquium. And those that come to this colloquium, I remind you what most, or actually, well, let me say all, and then you know that it's not true. All of the topological indices that we like to play with are just encoding, the topological indices encode some kind of a singularity, like in this combing hair theorem, that you have to have a singularity in this vector field in the tangential plane of the sphere. They encode in one way or another that there is some singularity in this alpha or beta of k. But we also know that if we take the Fourier transform of something with a singularity, then we cannot have exponentially localized wave functions. We know that the regularity of a function determines how fast the Fourier transform thereof falls off. So that kind of links these two things, right? The fact that I cannot write new orbitals of a band that are exponentially localized if I'm topological. I think that's a very important message, and we all should know that. Most probably we all knew that. But the moment there is a link between the localization of my Wannier functions and topology and the superfluid weight, I know that the superfluid weight will be bounded by something that is related to my topological index. And indeed, that's what people have derived over and over again. It, to my knowledge, started with the 2D Chern number by Sebastian in 2011, where he could show that the superfluid stiffness is bounded by the Chern number. And then you have prefactors that scale with the gap and things like that. But that's not just exclusive for the Chern number. You also have it in 1D systems for the 1D winding number. That was done by Murat in my group, and it's related to the winding number. And then now we have this fragile topology, which unfortunately is the one that is relevant for twisted bilayer graphene, or most probably should be relevant for twisted bilayer graphene. We have quite a lot of indications for that. Again, there is an index, and the superfluid stiffness is bounded by this index. And that's now beautiful, because now we started out from twisted bilayer graphene. We see this superconductivity, but then by just the trivial formula of 1/m star, we should think, but it doesn't react like a superconductor, because the superfluid stiffness should go to 0 when you have a flat band. But then the geometry of the band of your Bloch wave functions will kick back in a bit of stiffness. And it's not just kicking it back in, but it's bounded from below by an index which is integer valued. So with that, I would say all good, but not, because there is one issue, that all of this was based on mean field, because I derived this formula where the band geometry popped up by assuming some with the Jean ground state of my system. I made a mean field approximation to calculate my free energy, and now I have all these bounds relating topology to the superfluid stiffness, but there was an essential link where I used the mean field. Now, mean field is good when the interactions are not too strong, and in a flat band, kind of the only scale that there is interaction. So at least one should, carefully assess whether the mean field solution is any good. And that's what I'm going to do in the very last part of the talk today. And then we need to get this line out of our way, because this is annoying, because the name fragile topology by itself is delicate, right? Because topology was this thing that is stable, and now you tell me fragile, and really who came up with that word? And that well, we have to take it as it is and deal with it. And I think that's dealing with it is always the right thing. Then at least in my group, we run to the lab, we build a fragile system, and then we understand it, and we go back to, and do something beyond mean field. I think that's how we like to do it. Okay, now this is a crash course in fragile topology, and actually turns out something very trivial. Well, it's topological, but it's easy to understand. Now, a very simple topological manifold that are the tangential planes to the two sphere. Because I said that before, we all are taught at some point in our education that you can't comb your hair without a swirl, that you need to have a singularity in a vector field on the surface of a two sphere. So that's a topological manifold. Now I show you a trivial manifold. If your hair is more like mine and not quite tangential, but especially in the morning, going in all kinds of directions, the normal manifold to the two sphere is actually a trivial manifold, and you see from that very picture, right, that there is you're not bound to have a singularity in the vector field on that normal plane to the two sphere. So this is a trivial manifold, this is a topological manifold. Now if I put them together, then I can lift that annoying swirl that I have on the back of my head. I can just lift it and get rid of that singularity. So that's indeed the most trivial example of fragile topology, where you have a topological manifold, you add a trivial manifold, and the sum thereof is trivial. And in the band context, that just means I have a band which is topological, I bring in another band which is trivial, and together all of this is trivial. And at first you say, but bands don't just pop in out of nowhere, but especially in 2D samples, they actually do, because you might have your topological bands that you know and love, and then you tunnel couple, unfortunately, some other layer, and all of a sudden you have a band that trivializes your formerly topological band. So that's all I want to say about the magic of fragile topology. And now I want to give you, I give you here a crash course in many things that are much more complicated than what I say. But we can actually, we learned that if I have a system that is topological, I cannot find the basis in which of exponentially localized basis functions. So this we know, because you have to take a Fourier transform of something which has to have the discontinuity somewhere, and then you're not localizable. But we can turn that upside down, and we can say, okay, if it's localizable, if I can build my band structure from localized objects, then it's trivial. So now I'm not hunting for topological bands, but I'm hunting for trivial bands. And maybe I can make an exhaustive list of all the trivial bands by considering all the possible localized objects that I can place in all kind of places given my symmetries. Then I have an exhaustive list, and the moment you have an exhaustive list, then that's very good. And now that's the name of the game in topological quantum chemistry. You fix a space group, you fix some crystalline symmetry, then you take localized orbitals that perform under the symmetries in a good way, and you place them somewhere. And then the moment you place your well-defined orbitals in well-defined places in space, then it doesn't yet matter how they hybridize with each other. Not just any orbital content can occur in your Brillouin zone, because at the moment it's highly constrained. Given that you have a pz orbital here, you can't just get everything at the gamma point in your band. In fact, it's heavily constrained. And what you see coming over here is then, if you take this type of localized orbitals, you have to have this type of orbital content at high symmetry points in the Brillouin zone. That's just, it's just representation theory. But then you don't just put one type of pz orbitals at one location in the lattice. You just do a lot of hard work, and you place all kind of orbitals. That is A1, A2, B1, B2. These are just the orbitals of the local point symmetry groups, and you place them in all kind of positions in the lattice. That's 1A, 1B, 2C. This is just namings for high symmetry points in the lattice. And then you find which orbital content do I have to have in the Brillouin zone. And given the fact that now we have an exhaustive list of everything which is trivial, because I know by definition I induce this band from a localized orbital, and then I need to have this. And now I go do some numerical calculation of some sample, and I find this orbital content. Then I go, look, okay, at the end point, I have M5, so it has to be this or that or this or that. And then at the X point, I have X3 and X4, so it could be this. Or, oh, here it's already not compatible, so, oh, it has to be this. So at gamma, I have to have gamma 5. Just, oh no, I have here gamma 1 and gamma 4. So I already know that this band structure cannot be induced of any of these localized orbitals, so it has to be topological. And in fact, you can show that if you bring in the right trivial band, you actually can trivialize it, and it will be a fragile band. So that exercise I had to be explained many times, and then we could actually build it. So what you see here is again a 3D printed structure. It's a 2-layer system. What you see here is the plastic, but the plastic is what over here in the actual sample is air. So you should think of this, the air unit cell. So there's again these chiral channels. It's kind of a feature that we like. And then you go and measure its band structure, and you find exactly these M5, gamma 4, gamma 1, X3, X4, and you just built the fragile band structure. And I think to my knowledge, that was the first fragile band that was really carefully analyzed with the measurement data. It's also trivial in a sense for us with these acoustics. In the publication I cite here below, actually, the real punchline is that you have an observable signature of this fragile topology. It's not just doing the spectrum, but that's not the point today, because in the last few minutes, now that we feel much more comfortable with fragile topology, okay, it's topology that is as strong as any other. It's just better make sure not another band is kicking in. And now we can ask ourselves, okay, what is this bound that we've seen derived by very smart people, of course, but in mean field, and now we want to see whether this topological bound of the superfluid stiffness survives the going beyond mean field. And one has to say, I was not so fair towards mean field or Bogoliubov-Dechaine approaches, because in fact, in certain types of flat bands where you could think, well, the kinetic energy is reduced and reduced and reduced, so any interaction you add makes me like strongly interacting. So mean field is not exactly well tuned into that situation. Some people make a living of fractional quantum Hall states where that's exactly what you want, right? You want a flat band. There it also has topology, is kind of important. But and then you add a bit of interaction and all hell breaks loose. And for superconductors, it's actually that in the perfectly flat limit in certain lattices at 0 temperature, mean field is exact, but only at 0 temperature and only if you have the right constraints. And what we wanted to investigate is, does a honest-to-God numerically exact simulation show that this bound that is so important for the stabilization of superconductivity, and I come back to that in the next slide, can we prove that beyond mean field? And what we do, well, what we didn't want to do is to simulate a twisted bilayer graphene in a sense that unit cell is just super large, right? Because you have in this magic angle, you have a very huge unit cell. And then if you want to do numerics on that one, that we leave to the real professionals. But what we wanted to check is just give me a flat band with fragile topology where I know I have this bound. Is it surviving the step away from 0 temperature? And I think that's the real question we wanted to answer. And we did so in what people call the Kagome 3 lattice. It's again a hexagonal lattice where you see the triangles that don't have any crosses through them form this Kagome lattice, but just through the six-fold plaquettes here you're fully connected. So that's a lattice system that is not super obvious how you would induce that in a system, but here we really use it as a toy model. We add, again, we don't care who is binding our electrons together. We just give you an attractive interaction, so that will for free form your bosonic pairs, and then we check for the superfluid stiffness in quantum Monte Carlo calculations. Now the nice thing about the attractive Hubbard model is that you can do quantum Monte Carlo, and I just flash you the results. And what you see here is temperature. And then this is the superfluid stiffness, calculated for different system sizes. This has quite a lot of orbitals, so L equals 8 is already a substantial simulation. And you see how at high temperature you don't have any superfluid stiffness, as you would expect, and then it grows towards 0 temperature. And you see that arrow down here gives you that topological bound. So you know in the mean field limit at 0 temperature, where actually mean field is exact in this very model, you know that the superfluid stiffness is above this bound. And what we wanted to check is whether the moment you turn on temperature or other perturbations that I'm not going to show here, whether all these considerations actually go down the drain, or actually it survives. And for those of you that know 2D superconductivity, know that actually the superfluid stiffness plays a super crucial role, because we have a BKT transition that is controlled by how stiff your superconductor is. How hard is it to unbind the vortex-anti-vortex pairs? So the real TC of your superconductor you only reach once your superfluid stiffness is crossing this dotted line. So that gives a bit more importance to this calculation. And as I said before, this is the topological bound we would expect. And okay, we were happy about being able to confirm that indeed that bound that you derive in mean field also survives the step to a full calculation. And maybe it's surprising, maybe not. We were relieved that this was the case. And with that, I would like to summarize for today and again show you a bit of how we combine experimental work in today. It was only acoustics and not elastic waves, but it is kind of a playground where we know how to implement complicated models relatively easily. Either we have a challenge that is presented here where we say we would like to have these unidirectional channels, and we had to dig out how to do that, and then we're triggered into interesting questions that are also relevant for electronic systems. Or we pick up on experimental developments in electronic physics and do kind of that experiment more as a hobby for us to understand the new concepts in topology. Is even though it's free electrons or free particles and just wave physics, sometimes the modern concepts tend to overwhelm oneself by their not, yeah, by their apparent complexity, and if you have to cast it into an acoustic sample, that you know, then you have to see through all the not so complicated things, and yeah, that's what we do with our hand, that's what in our brain, and then our heart lies most probably somewhere in between. And with that, I thank you for your attention.
Thanks very much, Sebi. This was super interesting. Do we have questions? So maybe then I start, and after that you just go ahead and raise your hand. I wanted to ask kind of like a general question about this fragile topology. So you have this like nice explanation of it, that it's problematic if someone is a, say, device person and you want to study some interesting topology, but then you stuck it to the layer of HPN and suddenly the topology is gone. Do you know like how much of the topology is fragile? Like, is this something that should keep me up at night, or I can just like watch my topological modes as I would and don't worry about this at all?
Well, there are two answers to that, most probably many more. But first of all, you said topological modes. The truth about fragile topology is that you don't have obvious surface physics related to it. So already there, it's very different, right? It's only the fact that it's knotted up in any way. The fact that you can't localize it properly plays a role once you apply a magnetic field. So that's the first thing. The second thing, I would be more worried by the fact that this, well, the fragile topology in let's say, in twisted bilayer graphene is really stabilized by a symmetry, like many other of the topological insulators we have. And I think I would be more worried that by doing something on top or below, I break the C2T symmetry that is stabilizing this topology. I think you're more likely to get rid of the topological protection by breaking the symmetry rather than having another band trivializing your system. In the numerics, I think let me check. Yeah, in the numerics, we add more bands by adding orbitals at various places, and here we add a band that actually trivializes what is down here, and you do see that in the numerics you don't get any superconductivity anymore. Whereas if you add a band that adds another flat band that does not trivialize the system, the superfluid stiffness still goes up. So at least from an experimental, from a theoretical point of view, yeah, you should be worried about having other bands coming in, but experimentally most probably the symmetry is more delicate.
Okay, great. Thanks very much. I get it. I think Anton was next. Please go ahead.
Yeah. So coming back to the acoustic systems, you mentioned in passing. Let me see something. Yes. You mentioned the dissipation and the bandwidth being a big limiting factor.
Yeah.
So, do you have any thoughts? So, do you have any thoughts about that? And like, can one potentially improve and overcome dissipation? Does this make the application? Does this make the applications not really interesting, or like what role does it play?
I think I give you 2.5 answers. One is for applications in devices, I would always use elastic waves and not acoustic waves, because they are much more relevant also in terms of length scales and functionality, that you might have a Wi-Fi filter in your phone that performs better, stuff like that. So their dissipation is no real issue as compared to here. So it depends a bit which classical wave. So that's the first answer. The second answer is, yeah, if you insist on acoustics because it's a really trivial platform to play with, but you would like to get rid of the dissipation, you just make smooth walls. I mean, that's an observation. Dissipation, even in acoustics, is surprisingly hard to model, because at the end of the day it's Navier-Stokes. So but milling things out of metal rather than 3D printing it makes improvement in quality factor of a factor of 5 to 10. So that's a way to go if you want to do these kind of demonstrational experiments just with a narrower bandwidth. And then the last half answer is, I mean, we all know that dissipation can do really cool stuff in the like you can have non-Hermitian topology that kind of had nice features. The point is, acoustics is almost good for that. And I say almost because you have dissipation all over the place, but you also know that to get non-Hermitian topology out of these systems, typically the dissipation has to be structured. You shouldn't just have, it shouldn't just die. You should have, let's say, a sublattice dissipation, and you can engineer that. I mean, that's what we do at the moment in the lab. It's fine. You can do that. It's just, just because it's dissipative doesn't mean it's good for a non-Hermitian topology.
Oh, yeah, that part I appreciate. Yes. All right, thanks.
Titus?
Okay, I have one question that directly connects to what you just said. So when you showed the picture of this fan for the Weyl semi-metal, that's also on this slide coincidentally, I was thinking, what happens when you is there a way to make this spinning? Would there be something interesting coming out of that? I mean, I know people have looked at, I guess, active media churn insulators and so forth, but in the spirit of this non-Hermitian topology, is that one thing one could think about? And then I have another question which relates to the second part of the talk. Is very simple. This bound, I'm very surprised that you hit it so well, that your numerically obtained value is just a little bit above this bound, while this is just some mathematical bound. Do you, and the answer may very well be no, but do you know why this is so close?
In this case, I don't know why it's so close. Because this bound is not.
I mean,
high.
it's good. It's good. It's just. We have. We have other examples of other bounds that are much tighter even. So that's what I can say about here. It's just we were relieved to see that it's that we're better than the bound, and it's a bit better, but it's very close. I agree. And to the ventilator structure here, actually, this was Valerio's master thesis, and I told him, look, I want to have a Floquet type of magnetic field in a Weyl system. So why don't you put some ventilators, like some actually rotating things into a Weyl system, and we will get chiral channels. And then luckily he talked to Honi, and she told him, Honi always likes axial fields, right? So she said, but why you don't need to move any parts? You can do it with axial fields. And we were actually relieved because building in movable parts in these systems is a nightmare.